Alright, welcome. In this video I'm going to be working some second fundamental theorem of calculus examples and working through CalBC Homework 7.1. And so this one starts off with kind of a selection of drill problems like, hey, just take the derivative of this function that's already defined by an integral. What I'm going to do is I'm going to be careful though because, and the second derivative, so we're just practicing our derivative rules, right? I'm going to be careful because I know that a lot of these I'm going to end up having to write a tangent line for later, so I'm just going to leave room for that. Okay, so just get to it, I guess. Okay, integral 1 to x of e to the 2t square root of sine t dt. That does not look like something I'm going to want to take the second derivative of, but you know, I'm the one that made the homework. So what we do, remember to take the derivative of a of x. Still barely visible. All right, a prime of x is going to equal, I'm going to take x and I'm going to throw it wherever I see t in the integrand, which is the thing I've boxed off. So e to the 2x square root of sine x. Okay. And then I can take the, and times the derivative of x was just 1. Okay. A double prime of x, I'm going to need to use the product rule on this. But maybe I'll call that e to the 2x times sine x to the 1/2 power, so I can, look at it a little more easily, take its derivative. All right, so I'm going to start by taking the derivative of e to the 2x. That's e to the 2x multiplied by 2 for the chain rule. Leave this the same. Okay. Then I'm going to add in, leaving e to the 2x the same, taking the derivative of this. So that's 1/2 sine of x, leave the inside the same, to the negative 1/2 times the derivative of the inside, and that's the derivative of sine of x, which is cosine x. Okay, that's the second derivative. Okay, I know I'm going to eventually have to write an equation for a tangent line, so I'm going to leave some room. I might recommend you do the same. All right, for b, integral from 0 to x of t to the 4 dt. Whoops. Okay, then b prime of x is, I just throw in x wherever I see t in the integrand, which is in the box. So that's going to be x to the 4 times the derivative of x is 1. Okay, and then I'm going to take the second derivative by taking the derivative of x to the 4, and that's going to be 4 times x to the 3. And then, that's good. That's great. Right? We can do that. Okay, the C is looking a little annoying. It's all right. I'm just going to be kind of annoyed by some of these, but that's okay. It's just, there's a lot of problems here. 0 to pi over 2. I forgot to, no, not 0 to pi over 2. I wish. All right, integral from 0 to the sine of pi over 2x, right? Yeah. Of square root t dt. And that's going to be c of x. So what I'm going to do is I'm going to take this upper bound, throw it in wherever I see t in the integram, which is just there in the square root. So c prime of x equals the square root of sine of pi over 2x multiplied by the derivative of this, okay, the derivative of the upper bound, which is going to be pi over 2 for the chain rule, cosine of pi over 2x. Okay, we took the derivative of the outside, left the inside the same, and then multiplied by the derivative of the inside for the chain rule. And the second derivative of this thing, man, okay. I'll take the derivative of this one first. That's going to be 1/2 of that thing to the negative 1/2 times the derivative of sine of pi over 2x. But I already know that's going to be this, and so I'm going to leave that the same for the product rule, and so I'm going to just have that squared. And then we're leaving the inside the same, so 1/2 sine of pi over 2x. Okay. That's the first term in the product rule. Then I'm going to leave the square root of sine of pi over 2x the same, and take the derivative of this thing, which is going to be, okay, it's going to be negative sine of pi over 2x times pi over 2 again for the chain rule. So I'm going to have negative pi squared over 2 squared, because there's 2 pi over 2's, times the sine of leave the inside the same. And that was a really bad derivative. Okay, that's about as bad as I think you're going to encounter in this class. I think that's probably the worst we've had. Okay, that's C, and of course it's going to want me to, oh yeah, once I do the tangent line, it's not going to be that bad. Okay, but I'll do that later, and I'll need an extra sheet, I think. For part D, it's going to be the integral from x to x plus 2 of 4t. Okay, I'm going to change this one so it's more interesting, and I'm going to change it so it's, I think, 4t squared plus t. And if you want to do 4t plus t, then, you know, make that 5t be my guest. Okay, but that's not a very interesting problem, so I'm going to do it like this instead. So what's going to happen is I'm going to throw in x plus 2 in wherever I see this. So 4 times x plus 2 squared plus x plus 2. And then I'm going to multiply this thing by the derivative of x plus 2, but that's just 1, so I'm just going to leave that as it was. And then I'm going to subtract what happens when I throw x in, because x is the lower bound. So that's 4x squared plus x times the derivative of x is just 1 for the chain rule. So I've got this. That's cool, right? We can deal with this. And while a person could definitely, you know, distribute this and, you know, collect all of the like terms and honestly probably cancel off the 4x squareds and the x's, I'm not going to do that. So I can take the derivative of this object with the power rule. 8 times leave the inside the same, reduce the power by 1, multiply by the derivative of the inside for the chain rule, where that's just 1. Plus the derivative of x plus 2 is a 1, minus, this is going to be 8x to the first plus 1. So you can see that the 8x and the 8x are going to cancel, but it'd probably be easier for me to cancel after derivative taken than before in this case. Okay. E integral from 0 to x to the 3 of sine of t squared dt. Okay. And then e prime of x is going to be, I'm going to take that x to the 3 and put it in wherever I see t. So it's going to be sine of x to the 3 squared multiplied by the derivative of x to the 3 is 3x squared. Okay. That's x to the 6, and I think I'm actually going to write that in like that. So that when I go to take the derivative, the second derivative, right, I'm not dealing with even more layers of chain. That's going to be helpful for me. So I'm going to put my whiteout tape down, and so that's going to be x to the 6. Okay. So that e double prime is going to be, all right, I'm going to take the derivative of this one first because it looks easiest. I'm going to say that's 6x sine of x to the 6 plus, then I'm going to leave 3x squared the same. Derivative of sine of x to the 6 is going to be cosine of x to the 6 times 6x to the 5th for the chain rule. Fit one more on this page. Say f is going to be integral from negative x to x of t cubed dt. Okay, a person could realize that this integral is constantly 0, so its derivative is constantly going to, or this function, you know, defined by this integral, it's going to be constantly 0. So its integral is going, or its derivative is going to be constantly 0, but maybe we can see why that's the case. Okay, f prime of x equals, why is that? X to the third minus, when I plug in negative x, yes, negative x to the third, and then multiply by negative 1 for the chain rule because of the derivative of negative x being negative 1, that's where it's going to happen. I've got x to the third minus x to the third. Because you take negative x to the third power, that's going to be negative x to the third, but then multiply by negative 1. And I'm going to be subtracting a positive x to the third. And that's going to equal 0, always. Okay, why? How did you might be saying, like, wait, how'd you know that? And okay, here's the graph of y equals x to the third. It's an odd function, which means it has symmetry around the origin. And there is a property of odd functions that if you're integrating them over a region that's symmetric around the origin, you know, say I'm going just that far. And I go that far on the other side, x to negative x. These areas are going to balance out, right? I can say that this amount of area here is going to be the same as that amount of area there. And since they balance out, that area is going to be 0. That function is always 0. A 0 function has a 0 derivative. Okay. All right. And right, saving that for later when I got to come back and write these tangent line equations. That's f, and I've got 6 more, and I can do that. It might get worse before it gets better, but this is the practice that you need. Okay, g of x equals the integral from 2 to x squared of 1 over t to the third. I'm going to just call that t to the negative 3, if you don't mind, which I doubt you will. Okay, so g prime of x is equal to, I'm going to take that x squared and throw it in wherever I see t in the integrand. So that's going to be x squared to the negative third times the derivative of x squared with respect to x, and that's 2x. Okay. And I think I will simplify this because it'll make my second derivative easier to take. That's going to be x to the negative 6, because this is a situation in which we multiply our exponents, multiplied by 2x. That's 2x to the first. So that's equal to 2x to the negative 5. Okay. Making g double prime, just use the power rule, negative 10x to the subtract 1 from the power, and I get negative 6. That's cool. H of x is equal to integral 0 to 2x cosecant theta squared d theta. Remember, it doesn't matter what dummy variable we use. If we're going to take the derivative of this function, I'm still going to take that and throw it in wherever I see the dummy variable in the integrand. So that's going to be inside of the cosecant of theta squared. So cosecant of, now I do need to be careful and replace theta with all of 2x, right? So we're squaring that. And then multiplied by 2 for the chain rule, because the derivative of 2x is 2. All right. So now I'm going to, what am I going to do here? Yes, I think I'm going to rewrite this as 2 cosecant of 4x squared to make it easiest on myself when I'm taking the second derivative, you know, on a chain rule level. Okay, and so I will have h double prime of x equaling the derivative of, well, I'm going to factor out the 2 and just hold on to it. Okay, because the derivative of secant of x with respect to x is secant x tangent x. So that means that the derivative of cosecant u with respect to u is going to be negative cosecant u cotangent u. Okay, so I've got negative cosecant cotangent. We're going to leave the inside the same. And then we're going to multiply by the derivative of the inside. Yeah. That was kind of a lot, but it's good practice. Okay, j of x equals the integral from x plus 2 to 0 of t cosine t dt. Okay, this one I might recommend shifting it to make it the negative of the integral from 0 to x plus 2 if you feel like that. Or you could just say, I know that, okay, it's going to be minus because it's in the bottom. Throw in x plus 2 wherever we see t in the integrand. Cosine of x plus 2 times the derivative of x plus 2 with respect to x is just 1, so I don't have anything else to worry about. That's j prime of x. Okay. meaning j double prime of x is going to equal product rule. I'm going to look at it as a product of this thing and that thing. So I'll take the derivative of this first, and that's going to be -1 times, leave that the same, plus, then I'm going to leave that the same, and take the derivative of this, which is going to be negative sign, leave the inside the same, multiply by the derivative of the inside for the chain rule is just 1. Okay, so you could call that plus x plus 2 sine of x plus 2 if you wanted. All right, and then that's, okay, that's second derivative. I'm good. Continuing to move. K of x. This one's got both bounds variable. I do like how this has got it's got the full range of everything that we could possibly see. And that's what I aim for with these homeworks. Okay, k prime of x is going to be, I'm going to throw in x to the 3 in for t. That's going to be x to the 3, but then I'm going to have to multiply by the derivative of x to the 3 for the chain rule. And that's 3x squared. Then I'm going to subtract, doing the same process with the x squared in for t. So I've got x squared in for t multiplied by the derivative of x squared is 2x. And to make this easiest on myself when I go to take the second derivative, I don't have to do product rule twice, end up with 4 terms. I can just combine these using algebra, right? And call that 3x to the 5 minus 2x to the 3. And then k double prime will equal 15x to the 4 minus 6x to the 2. So m is going to equal the integral from 0 to 3x minus 2 of the square root of t squared minus 4t with respect to t. Okay, so m prime is going to be, I throw in 3x minus 2 wherever I see t in the integrand, which is that square root. So square root of 3x minus 2 squared minus 4 times 3x minus 2, that wasn't enough roof over my square root. And then I need to multiply by the derivative of this for the chain rule, so that's times 3. All right, I'm thinking that a person could use layers of chain here, outside, middle, inside, or I could say that this is 3 times the square root of, that's going to be 9x squared minus 6x minus another 6x is minus 12x plus 4 minus 12x plus 8 to the negative. No, positive 1/2. All right, so that m double prime of x is equal to, do the power rule on the outside, 3/2, leave the inside the same, 9x squared, I'm going to make that minus 24x, and plus 4 plus 8 is 12. Okay, and, you know, a person could factor out a 3 from there, but I don't feel like it, so I don't need to. And then I multiply by the derivative of the inside, which is feeling like 18x minus 24. It's another thing that we could factor out on, but we don't need to do that. Okay, that's m. I've got one more of these type of problems. I'm going to call that n of x equals integral from 0 to x to the 3 of 1 over 1 plus t squared. Okay, this is an antiderivative that we need to know. Okay, the antiderivative of 1 over 1 plus t squared with respect to t is going to be inverse tangent of t. And I'm not going to need that for this problem, but I do need to remind you that that's something you are expected to know. All right, so now I've got integral 0 to x to the 3 n prime I'm trying to take. So that's 1 over, wherever I see t in the integrand, I'm going to plug in x to the 3. So 1 plus x to the 3 squared multiplied by the derivative of x to the 3 is 3x squared. I'm going to rewrite this so that when I take the second derivative, it's not so bad. 3x squared divided by 1 plus x to the 6. And just in time, I got this. Okay, I felt like this set of drill problems had it all, but it didn't have the quotient rule. But now it does. Okay, so I've got n double prime equaling bottom derivative of top minus top derivative of the bottom divide by the bottom squared. I've heard some people are starting to forget their quotient rule, and don't let that be you. I don't need you forgetting. In fact, I need you to not be forgetting your quotient rule as we move forward through the course, because it's going to come back every now and then, situations where you wouldn't expect, right? Right here. You thought we were moving forward, doing more integrals, not more derivatives. But here we are, practicing our new derivative rule. So write the first and second derivative of each of the functions. Write an equation for the line tangent to the graphs of b, c, d, f, g, k, and n at the point where x equals 1 without the use of a calculator. And then use a calculator to write tangents to the graphs of a, e, and j at x equals 1. All right. B. So I need a point. My point is going to be, well, x is 1 and y is going to be b of 1. So the integral from 0 to 1 of t to the 4 dt. Okay, I can do that maybe up above. I'm going to increase the power by 1, divide by the new power, plug in 0 and 1, and subtract. It's going to give me 1/5 minus 0, and so that's going to be 1/5. Slope, I already have an equation for b prime, so that's helpful. That's x to the 4. Slope is 1. The equation is going to be y minus 1/5 is equal to 1 times x minus 1. And that was b. C. Well, I'm going to have to do that up above, I guess. All right, so at x equals 1, my point is going to be, okay, the integral from 0 to sine of pi over 2, okay, pi over 2 is up there, sine is the y-coordinate, that's going to be 1. So now I'm integrating from 0 to 1 of the t dt. So I'm going to write that as t to the 1/2. Okay, and I can do that up above. And that's going to be 2/3 t to the 3/2 as t runs from 0 to 1, which is 2/3 of 1 minus 2/3 of 0. Okay, so it's going to be 1 and 2/3. Okay, the slope on C is the square root of sine of pi over 2x. Okay, I've already computed that. That's 1. So square root of 1 is still 1 times pi over 2 times cosine of pi over 2 is 0. Okay, so this was not very interesting. This is going to, if it's got a flat slope, then it's just a y equals, so it's y equals 2/3. Okay, or you could say y minus 2/3 is 0 times x minus 1 if you wanted to do that. That's fine too. All right, that was A, B, and or B and C. I got to pull out D. I think I'm going to actually take a break and eat my lunch and resume this in a few minutes. All right, so I'm going to get a point and a slope. Okay, so the point is going to be x is 1 and y will be the integral from 1 to 3 of 4t squared plus t. Again, dt. If you were working this as it appeared on your homework, you would be integrating 5t dt from 1 to 3, and that would give you a different answer, but I feel like this will be more interesting if I do it like this. All right, so that's 4/3 t to the 3rd plus 1/2 t squared as t runs from 1 to 3. Ooh, that might have been a mistake. What's up?